The point of the problem is to find the moment of inertia of a stick of length L about an axis through its center of mass without using any calculus. So what is to be used? There are two ideas. One is the scaling argument. What is that? So if you figure out what this moment of inertia depends on using dimension analysis, ask what would happen to the moment of inertia if the length of this stick was to be doubled. Then this moment of inertia out here would be some number times I naught. So if you figure this number out, that is one part of the problem, and that is using the scaling argument. The second part is to use the parallel axis theorem, which tells us that if we know the moment of inertia about center of mass, then we will be able to shift it to any new axis. Put the two ideas together and you should be able to figure out what is this moment of inertia. Also think about extending this idea to other shapes. Let us call this moment of inertia I naught. We are interested in looking at its dependence on the length L because we are going to double it and figure out what is the moment of inertia for the new rod. When you double the length, the one thing that stays a constant is the density. If you look at the definition of moment of inertia, we need to take a small mass at a distance x from the axis we are interested in, and the moment of inertia would be given by the mass into the square of its distance from the axis. Since density is a constant, we can write this mass dm as density into the small length dx, where that is the small length dx. So this can be rewritten as density into x square dx. Density being a constant, as we increase the length of the material, we have to look at the behavior of x square and dx. Both have dimensions of length. And the only parameter in the problem which has dimensions of length is the length of the rod. And therefore, this must be proportional to the length of the rod to the power of 3. And therefore, if we double the length to 2L, then the moment of inertia of that rod would be proportional to 2L the whole cube. Therefore, we can say that I is going to be 8 times I naught. The second idea we're going to use is to figure out this moment of inertia out here in terms of the moment of inertia I naught by using parallel axis theorem. If you look at this half, it is of length L, therefore is just like this rod. So about its own center of mass, it would have a moment of inertia which is I naught. Similarly, about this axis, it would also be I naught. So let's use parallel axis theorem now. I naught plus the mass of the object, which is given to be m. Therefore, if you want to shift it to this new axis, this distance being L by 2, we could write the new moment of inertia as I naught plus ml by 2 whole square. For one side, there are two of them, therefore that must be multiplied by 2. This is by scaling theory, and that is by the parallel axis theorem. They have to be identical, so we shall equate them. 2 times I naught plus ml square by 2. And that implies that the moment of inertia I naught is ml square by 12. Now this is the moment of inertia we would have arrived at if we had carried out this integration. So use this on other objects. We realize that when we double the length, that object must be made out of the smaller one. So if we consider an equilateral triangle or a square, we can see that they're made up of smaller triangles or smaller squares. So this equilateral triangle is made up of 4 smaller triangles, and similarly the square is made up of 4 smaller squares. So this idea of scaling can be taken on to these objects. You can also use it on a 3-dimensional cube. It can also be used for a fractal triangle, and that will be the topic of another video.